Hello, in 6.8 we're going to introduce L'Hôpital's rule as a way of solving certain indeterminate forms. So what is an indeterminate form? So let's first look at two particular types of indeterminate forms. So the first type that we're calling the type 0 over 0 is a limit of the form f of x over g of x, where both the numerator and denominator go to 0. So an example of this type maybe is a limit of the form, the limit as x approaches 0 of sine x over x. Right, we've seen this limit before back in Calculus 1 when we were deriving the formulas for the derivative of sine and cosine. We used this limit. We showed that this limit is equal to 1, but it's in that 0 over 0 form because we see that the numerator and denominator both go to 0. So it's in that 0 over 0 form. But of course we see that we know that this limit actually has a value of 1. We went through some geometric argument to make that to show that that limit is equal to 1. Another example might be a limit of the form simply limit as x approaches 2 of x squared minus 4 over x minus 2. Again, you see the numerator and denominator both go to 0. But we can do some algebraic manipulation in this case to solve it. As you could factor the numerator, x minus 2, x plus 2. X minus 2 divides and we get the limit as x approaches 2 of x plus 2. So we see this limit was originally in that 0 over 0 form, has a value of 4. But it's a indeterminate form 0 over 0. And it's worth noting here that in either of these cases we got different outcomes. So 0 over 0 really is a form that can come out to be anything. So indeterminate really means that there's no determined value for this. It could be any value. We'll see something similar with the infinity over infinity form. So an indeterminate form of the type infinity over infinity is a limit of the form f of x over g of x, where both f and g go to some form of infinity. Okay, so it could be positive or negative infinity. So an example of this might be a limit as x approaches infinity of x squared minus 2 over x squared plus 4. Here we can manipulate this one algebraically to get the form, but we see it goes to infinity in the numerator, infinity in the denominator. But the value of this can be solved by manipulating it a little bit. Just dividing out the x squared. We see that rewriting it in this form, now as x goes to infinity, 2 over x squared goes to 0, 4 over x squared goes to 0, so we're just left with 1 minus 0 over 1 minus 0, so it's 1. But it started out in this infinity over infinity form. And yeah, we can also think of many other examples. Take for instance an example like this, where you've got the natural log of x over x minus 1. Taking the limit as x goes to infinity, both the numerator and denominator go to infinity. So how would we evaluate this limit? Well, we're going to develop some tools in a moment to help us evaluate this limit. And in fact, the main thing is recognizing these two forms. If I have a limit that's in this type 0 over 0 form, or a limit that's in this type infinity over infinity form, then we'll be able to use L'Hopital's rule. And it'll make evaluating these kind of limits very, very easy. So here let's read what L'Hopital's rule says. Suppose f and g are differentiable, and g prime of x is not 0 on some open interval I that contains a, except possibly at a. Moreover, let's suppose that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches g of x is also equal to 0. So in other words, it's in the 0 over 0 form, right? Or that the limit as x approaches a of f of x is either positive or negative infinity, and the limit as x approaches a g of x is positive or negative infinity. So it's also possible that we can use the rule when it's in that infinity over infinity form. Okay, so it must be in one of these two forms. So it's either in the 0 over 0 form, or it's in the infinity over infinity form. In which case, then we can evaluate the limit of f of x over g of x simply by taking the derivative of the numerator and denominator. And what that oftentimes does is it simplifies the limit into a form that's more easily evaluated. So let's just practice this a little bit. So I wrote this limit earlier, the limit as x approaches 1 of ln of x over x minus 1. Actually, sorry, this is a little different. This is not, this is of the 0 over 0 form. So it's not going to infinity, it's going to 1 here. So that's important that we look at this carefully, right? Is this in one of those 0 over 0 or infinity over infinity forms? We want to always check to make sure it's in one of those forms before we apply the rule. In this case, yeah, we can see that as x goes to 1, ln of x goes to 0, right? So ln of 1 is 0, and downstairs we'll also have 1 minus 1 is 0 downstairs. Since it's in the 0 over 0 form, means we can apply L'Hopital's rule. And it's important that we always check this first, otherwise we could make some very bad mistakes, because it really only works when it's in one of these forms. So yeah, we can apply L'Hopital's rule. Okay, so L'Hopital's rule says that if I take the derivative of the numerator and denominator, we get the same limit. Notice that we're actually not doing the derivative of the whole function, but we're doing the derivative of the numerator and denominator separately. So I'll take the derivative of ln x in the top, which is 1 over x, and the derivative of the bottom, which is just 1. And here to kind of indicate that I'm using L'Hopital's rule, I'll just make a little note over here to remind me that going from this step to this step is where I'm applying L'Hopital's rule. And then just evaluating this now is much simpler, right? The limit as x approaches 1 of 1 over x is 1. How about this limit? The limit as x goes to infinity of e to the x over x squared. Now, as x goes to infinity, e to the x goes to infinity, and x squared also goes to infinity, so we see it's in the infinity over infinity form. So it's in a form where we can use L'Hopital's rule. So in the next step, we can say that this is equal to the limit as x approaches infinity of When I take the derivative of the numerator, we get e to the x again. When I take the derivative of the denominator, we get 2x. Right? So there I applied L'Hopital's rule. However, the form that we're in is still in that infinity over infinity form. There isn't much I can do algebraically to simplify this, but it's still in the infinity over infinity form. So as long as it stays in this form, or in the 0 over 0 form, I can keep applying the rule. So here I was in the infinity over infinity form, so I was able to use L'Hopital's rule. Here it stayed in that form, so I can use the rule again. So we'll do it one more time. Let's see what happens now. Again, I'm going to make note of it here. We're going to get the limit as x approaches infinity of the derivative of e to the x will be e to the x. The derivative of 2x will be 2. And now I get something that approaches infinity in the numerator but stays 2 in the denominator. So this will be infinity over 2. So it'll just be infinity. So in a sense, what we've shown is that the numerator of this expression, e to the x, grows much more rapidly than x squared. Let's try another example here. The limit as x approaches infinity of ln of x over the cube root of x. So again, we're kind of comparing the growth rates of these two functions. Now, let's check to see if it's in the correct form. So again, I notice as x goes to infinity, ln x goes to infinity. So here it'll be infinity in the numerator. And the cube root of x also goes to infinity. So it's in the infinity over infinity form, so we can use L'Hopital's rule. So taking the derivative of the numerator and denominator, again we know the derivative of ln of x was 1 over x. And the derivative of the cube root of x, well, let's think of that, that's like x to the 1/3 power. So thinking of it this way, we'll take the derivative will be 1/3 x to the negative 2/3. So we might notice that after we've done it this first time, right, this limit will be something that now looks like it's in a 0 over 0 form, but actually I have to be careful. Do I need to keep applying the rule? In some cases, we may be able to avoid having to reapply the rule again just by simplifying it. I notice that there is some basic simplification that can happen here. So let's go ahead and do that first, and then see what we have to do. So let's see, I would have 1 over x, and then here I'll multiply the 3 in the top. X to the negative 2/3 comes to the top as well, as x to the positive 2/3. And then dividing x to the 2/3 by x, we get 3 over x to the 1/3. And now looking at this, I see that as x goes to infinity, we get something that stays 3 in the top and goes to infinity in the denominator. So now it's just going to be 0. So we didn't need to reapply the rule again. We just had to simplify what we had after the first step. And then we got it into a form that we could just easily evaluate.